me the chance to give this presentation. So I decided to talk about quantum noise. Okay, so I decided to talk about quantum noise because for two main reasons. Quantum noise is a very interesting noise. First of all, because this is one of the main limitations both to current and to future gravitational wave detectors. So you see here, put the noise budget for advanced Virgo, which is very similar to the one of advanced LIGO. Quantum noise is represented by the purple line, and you see that it's limiting the sensitivity at almost all the frequency. And for Einstein telescope and also Cosmic Explorer, the situation is very similar. And the second reason why I think quantum noise is interesting is that it is intrinsic connected to the interferometric measurement that we are performing. So if you consider the challenge to measure gravitational waves, it is like to being able to detect a small displacement of the test masses against all the disturbances that creates spurious displacement of the mirrors. And if you imagine that you are able to shield the mirrors from all this displacement, remove thermal noise, seismic noise, even if the mirror are perfectly still, then you still will have this limitation that it gives from that it comes from quantum noise, because it is really connected to the interferometric measurement itself. We'll organize this presentation. The first part is about describing what is the origin of the quantum noise, and then what are the strategies that have been put in place to mitigate it. When it comes to quantum mechanics effect on gravitational wave detectors, you might think of two main mechanisms. The first one is the quantum nature of the light that is used for the measurement, and the other one is the quantization of the test mass itself, the mirrors. So in this presentation, I only focus on the first one, because actually it was demonstrated that the second one is not relevant as we are measuring a classical force. So this has been stated that this is the reference that describes why the only quantum noise that we should consider when it comes to a gravitational wave measurement with interferometer is the one that is coming from the quantum nature of the light that we use. So usually quantum noise is presented in what is called a semi-classical picture. So this picture has some advantage. For example, it's quite intuitive, and also it provides, of course, the good result. But it also has a very strong limitation, especially when it comes to understand how we can mitigate quantum noise. Anyway, we'll go on just briefly describing this, and then we will move to a complete quantum picture that will allow for a more deep comprehension of the phenomenon. So usually quantum noise is, we can distinguish two contributions. One is shock noise and the other one is radiation pressure noise. So the idea is that the laser is composed by photons, and what we do is actually counting these photons. So we know the interferometer is something that is converting a displacement of the test masses into a change in the power of this output, and we want to measure the arrival rate of this photon and a change on the power of the output on a photodiode. But if the photons arrive not equally spaced, so we will have a jittering, so we will have a noise. This is what happens because actually photons are, the arrival of photon is a stochastic process that follows Poissonian statistics. So we have a counting noise that is proportional to the square root of the power. Actually, the signal that we measure is proportional to the power itself. And so in the end, the signal to noise ratio, which is what matters, scales as the ratio of the square root of the power. So we can reduce the effect of quantum noise by increasing the power. But then at low frequency, we have radiation pressure noise. And this is the same phenomena, but it's the same fluctuation in the arrival time of the photons, which transfer a momentum, stochastic momentum on the mirrors. And so it brings displacement noise, which is more important at low frequencies. So this is because the mirror are suspended, so the reaction to a force is less and less important when you go high in frequency. So there is a dependence that is 1 over f to the power of 2. And this determines the fact that at low frequency, radiation pressure noise is more important, while at high frequency, shot noise is more important. So here you see a plot that shows what happens when we increase the power. So we have quantum noise. It is composed from the sum of shot noise, the flat one at high frequency, and radiation pressure noise at low frequency. If we increase the power, we will simply shift this curve. So blue one will have a reduced shot noise and an increased radiation pressure noise. In the end, all the minima of these curves will all lies on this green curve that is the standard quantum limit, and that only depends on the length and on the mass of the length of the arms and on the mass of the mirrors. What is very interesting is that we have this limit that comes from Heisenberg principle. We will see this in details. But unlike Heisenberg principle, it can be circumvent. So it's not a fundamental limitation for our measurement. So a complete quantum picture, the one that we will allow that to understand better how quantum noise is originated and how to mitigate it, was provided first time by Caves in the 80s. So at that time, there was a controversy on the fact if the radiation pressure was not having an effect, was having or not an effect on the interferometric measurement. He solved this controversy and actually demonstrating that it does. And then he proposed this new picture to explain quantum noise in interferometers. So this is the reference of this very important work. As I said, we need to switch to a complete quantum representation. So the first ingredient, we have to consider a quantization of the electromagnetic field. So in this case, amplitude and phase are regarded now as quantum operators. And then we need to consider some particular quantum states that are the coherent state. So for this state, amplitude fluctuation and phase fluctuation, I mean the product of the uncertainty on the amplitude and on the phase is the minimum allowed by Heisenberg principle. And the reason why we care about these states is that both vacuum and laser can be described as coherent states. So this is a very important point, is the fact that even if to us they seem very different, actually they are the same state, and the only difference between a vacuum and a bright state, so a laser, is that in a phase amplitude plane, so this uncertainty circle is translated, so there is a bright carrier, but for all the other things, especially for what concerns their noise feature, they are exactly the same. Caves, he realized that since the interferometer is operated in the dark fringe, all the common noise that are injected from the bright port and also common motion are not relevant. What is really relevant are the noises which are differential. So for example, the noise that are injected from the antisymmetric port. So as I said before, vacuum fluctuation has the same fluctuation of the light, but since they are injected, they enter the antisymmetric ports, they are the one that after recombining with the laser inside the detector actually enforce quantum noise. And this is quite impressive, because in the end, all the measurement is limited by the fact that we have vacuum that we cannot avoid entering the interferometer from the unused port. He also understood so that the key solution to mitigate this noise rely on modifying this vacuum to make him less harmful. Actually, he understood that we can surpass, overcome, go beyond the standard quantum limit if we are able to introduce some correlation between amplitude and phase fluctuation. So there are many ways to do this, but the most straightforward way is to prepare what is called a vacuum squeezed state and inject it in place of the normal vacuum state. So a squeezed state is
Eleonora, we lost you. I think you're muted or.
Sorry.
Oh, okay, sorry. It's okay. You're back. Maybe
Okay.
it's me, but
Okay. Sorry. So did you hear me up to here?
yeah, that's good. Yeah, you can start from here.
Okay, so I was saying that I was describing a squeezed state, saying that it's actually a state in which the uncertainty in the amplitude and in the phase are reorganized. So we can actually reduce uncertainty, for example, in the phase at the expenses of the one on the amplitude. And this is because the product has to stay constant because it has to be compliant with the Heisenberg principle. So a squeezed state is characterized by a squeezing factor, which is actually the magnitude of the squeezing, so how much it is compressed, and also squeezing angle, which is the orientation of the ellipse. And so, as I said, the idea is just actually we replace this squeezed state, the ordinary vacuum with this state. So this is a simple sketch that shows, for example, if you have in ordinary condition, your gravitational wave signal will be actually superposed to the phase noise, that is the blue arrow in this scheme. So in case you are injecting a squeezed state, so your phase fluctuation is reduced, gravitational wave signal will have to, will be more important with respect to the phase noise, and so the signal to noise ratio will be improved. And this is also what is shown here. So this is a very simple simulation. We have a simple Michelson interferometer. One of the mirrors is modulated in order to mimic a gravitational wave, the effect of a gravitational wave. So at the output photodiode, see the signal in time. In the first case, we can barely see a signal because of the scattering of the measurement shock noise. But when you inject the squeezing, you see the signal become much clearer. So, so this was the proposition of Cales. I think it's very interesting to what he wrote in the conclusion of his paper, because this squeezed state at that time were something that were never produced. So were just hypothetical ideas. And he wrote that he understood that probably this will be very difficult to create, actually to produce a squeezed state, but difficult or not, it might turn out to be the only way to improve the sensitivity of the interferometer at some point. And he hands off the responsibility, the task to the experimental physicist, saying that they might then be forced to learn how to very gently squeeze vacuum before it can contaminate the light in the interferometer. So this seminal work opened the path to many years of technological development. And this is a plot that shows how much the expertise on squeezing improved along with the years. So the first demonstration happened in 1985. And then now we are able to measure up to 15 dB of squeezing. So usually squeezing is measured in dB. So it's a logarithmic ratio between the standard noise of a ordinary vacuum state and the one of a squeezed state. Actually, this plot is missing an information because the squeezing that is useful to gravitational wave detectors has to take place in the relevant frequency region for the detector, which is between 10 Hz and 10 kHz. So this plot, maybe it's a bit more difficult to read, but actually it is a plot that also shows the performances of the squeezing as also with respect to the frequency, the frequency of the measurement. So this chronological order follow the alphabetical one. So A is the first measurement. That's very low squeezing, very high frequency. And then little by little, we managed to go down in the squeezing level and also in the frequency. So it's important to remark that, as usual, make a good measurement at low frequency is more difficult because there are a lot of technical noise which are more difficult to get rid of at this low frequency. Just to say 2 words about how actually the squeezing is generated. So it's something that concerns the nonlinear optics. So what we do, basically we make interact a laser with a non-linear crystal, which is able to create the correlation between amplitude and the phase of the light state. So here is a very simple scheme. There is a laser. First thing, it has to be double in frequency with a second harmonic generator. Usually the laser for gravitational wave detector is infrared 1064 nanometers, so the second harmonic is green, and become visible, so it's nice to see. And then it is used to pump this optical parametric amplifier, that is the one that is actually producing squeezed fluctuation. So if the OPO is pumped below a certain threshold, what we will have at the output is vacuum squeeze fluctuation that can be sent to the interferometer. Just to give you an idea, this is a real squeezing bench, how it looks like. So the top one is the one that is actually installed in Virgo, so it's a lot of optics. The dimensions are quite small, so it's maybe 1 meter by 1 meter. And the one on the bottom is another squeezing source that we have developed in Japan for a test bench. I put the picture because you can see the green light, as I mentioned before. Okay, so the first application of, already 10 years ago, it was the technology was mature, and we could apply the squeezing to real detector. So the first test was done on GO600 and also on initial version of LIGO. They were kind of pioneers of this technique. You can see that the improvement in the sensitivity is visible, even if it's quite modest. And this brings us to another very critical point of the squeezing, that is the fact that it is very fragile. So not only the production is quite complex, but once we have produced it, we also should take a lot of care not to destroy it. So the main enemy of the squeezing is optical losses. And this is because every time a squeezed state, I mean vacuum squeezed state, cross optics or experience an optical losses, we have to consider that it will recombine with a non-squeezed state, which will degrade a squeezing feature. So this is a plot that shows, for example, if you have injected squeezing, an amount of injected squeezing, what is the squeezing that you can actually measure, given an amount of losses. So for example, you see, for example, the green light is what corresponds to 30% of losses. And you see that no matter how much squeezing you inject, you will never be able to measure more than 5 dB. And another important source of squeezing degradation is the phase noise. This is a jittering of the squeezing ellipse. In this case, we have to be even more careful, because if of course, we measure on one axis, which is usually the one with the on the shortest arcs of the ellipse. But if the ellipse jitter, then the projection will be no longer the smallest one. And if the squeezing level is very high and the noise is very large, we might even end up with a noise which is larger than the one of the ordinary vacuum. So phase noise can be very dangerous. Okay, so after this first test, finally between O2 and O3, so at the beginning of O3, squeezed sources have been permanently integrated both in LIGO and in Virgo. And it was a very nice result, brings an improvement in the sensitivity that you can see from this plot. The improvement was about 3 dB, and we estimated losses between about 25% in LIGO and between 30 and 40% in Virgo, quite high. But it had to improve the detection rate up to 50%, for example, in the case of LIGO. So this is, as I said, a very good result. What is coming next? So if you look at this plot, you can see that basically squeezing can improve the noise only at high frequency. I mean, at high frequency, only starting from 50 Hertz. And at low frequency, you can see even a tiny reduction of the sensitivity with respect to the case without squeezing. And this is a very crucial point, because the squeezing that we inject, that is called frequency independent, is actually actually only able to improve the sensitivity where the spectrum is dominated by shock noise. And this is because the ellipse is oriented in a certain way, but once it is injected into the interferometer rotates it, and so at low frequency, it is no longer oriented in the good direction. So what to do? In order to have a broadband quantum noise reduction that corresponds to the green curve in this plot. So orange curve is the standard quantum noise. Then if we inject frequency independent, we can improve high frequency and make low frequency worse. And then if we want to have a broadband quantum noise reduction, we should prepare and inject a squeezed state, which has an angular dependence on the frequency. So this is what we are working now. The idea is that this frequency dependent can be imposed by reflecting the squeezed state by an optical cavity. It's usually called filter cavity. And of course, this will bring some difficulties because the cavity has to be very low losses. The line width has to be very small because the rotation takes place at very low frequency, about 50 Hertz. And so it has been it need a long work in order to be able to obtain a rotation so low without degrading the squeezing too much. So it was first, I think, Kimball in 2000, which had this idea of the rotation of the squeezing ellipse. And at the first time, it was realized in the megahertz region in 2005, and then more recent in kilohertz region. And just last year, it was finally demonstrated below 100 hertz, which is actually what we need to actually apply this technique to gravitational wave detectors. So the technique of frequency-dependent squeezing is now mature, and it has been implemented both in LIGO and in Virgo, and we hope it will be operative for the next observation run. So this is the case of Virgo. I put this because I'm actually working on these topics in these days, and like this is very similar for LIGO. So we have built a 300-meter filter cavity, which is a side of the north arm of LIGO, of Virgo. And the commissioning of the filter cavity is ongoing. So we are now we have just installed the suspension of the mirrors, and we hope it can be operative when the fourth observation run will start in 1 year. So what's next? Very briefly, squeezing will be also a key technology for third generation gravitational wave detectors. If you look at the Einstein telescope sensitivity, you will see that it relies on the ability of reduced quantum noise of 10 dB. This is quite large amount, and it means that we need to have losses, overall optical losses below 10%, which is quite a good result. And also in the design of Einstein telescope, 2 filter cavities are planned for the low frequency interferometer, and 1 for the high frequency. So there are some challenges that we have to face in order to be able to fulfill this requirement. We need to, for example, learn how to produce a stable and performant squeezing source at different wavelength, the one that is likely to be used for Einstein telescope. And then we have to reduce the overall amount of losses, and to learn how to make filter cavity which has a rotation at very low frequency. And of course, this is what up to now is considered the most well-established and effective way to reduce quantum noise. But even in the past, there are many other strategies that have been proposed. So maybe I don't have the time, but I would like just to mention this one, which very recently has drawn the interest of the community. And this is actually relying on a more fancy way to produce frequency-dependent squeezing. It will make use of 2 EPR entangled beam, which are one detuned in frequency with respect to the other, and they are injected to the interferometers, and so this will, will allow to produce a frequency dependence without the use of a filter cavity. So the arm cavity itself will be seen as a filter cavity from one of the two beams, and then by conditionally make a conditional squeezing measurement of one of the two beams, we can have we can find the information and reduce the noise in a frequency dependent way, so improve quantum noise on all the frequency. But this is just an example to to show that the fact that the squeezing up to now has been the most studied and developed technology doesn't mean that maybe we will find in the future a smarter and a clever way to improve quantum noise. Okay, so I think I finished. So just a few points to summarize what I said. So first of all, I presented the quantum noise, which is very interesting as it is an intrinsic limitation of the interferometric measurement, and it is originated by vacuum fluctuation which enter the antisymmetric port of the interferometer. And then second, I presented standard quantum limit and I said that this is not a ultimate limit for our measurement, and it can be actually circumvent if we are able to create a correlation between amplitude and phase fluctuation of the vacuum that is originating the noise. And up to now, the most effective strategy to do this is the squeezing. So there were many research and many technological development that brought the squeezing to be a very well-established technology and a key feature of present and probably future gravitational wave detectors. But in any case, there is an open field and many other strategies that are being studied to provide possible clever and more effective solution to this problem. I think that's all.
Thanks a lot, Eleonora. Is there any questions for Eleonora? You can raise your hand. We have time for one or two questions. Okay, so if not, I have one actually. So sorry, I didn't quite understand. So today in the current design of the sensitivity of Virgo LIGO, you're already hitting this limitation of quantum noise at low frequency, or you're not there yet? Because it seems in your first plots that you have a higher limitation. I mean, you have Newtonian noise or things in the one of the first plot. Oh, you see it, okay.
Actually, radiation pressure noise is not yet limiting the the sensitivity, but we were already able to see a small degradation of the performances that is due to the fact that anyway, even if it's not limiting, it is anyway increasing. So there are this paper that has been published recently that show that demonstrate the fact that the increasing in the radiation pressure is already visible in the performances of the interferometer. And another way to understand that this problem is actually already present is that, for example, in the case of LIGO, when they inject the squeezing, they found that the optimal angle, of course, the fact that you have a frequency independent squeezing doesn't mean that you cannot have a fixed angle on all the frequencies. So normally the squeezing ellipse is oriented to have the shortest axis with the gravitational wave signal, but you can also think to rotate it in a frequency independent way. And so they found out that the optimal angle was not the one on 90 degrees as the one would expect if you only want to reduce quantum noise, but there was a small angle. I mean, if you rotate it by a small angle, it's the sensitivity improves, and this means that we have an effect at low frequency coming from radiation pressure.
Thanks. Yeah, thanks. Okay, so I don't see any hand raised. So
I have one quick one.
Oh, okay, sorry.
I don't know how to answer.
Yeah, please go ahead.
Okay, so it's very naive. So I haven't quite understood how you actually produce the squeeze vacuum state with the phase that you.
Yes, this is one of the
I
most.
understood like roughly with the yeah, it was I think around 16, 17 slide.
So maybe this is I prefer. So this is another picture that show maybe a bit better. So we have a nonlinear crystal. So the nonlinear crystal has polarization which depends on the also quadratically of the amplitude of the electric field that is injected. So so what we do is we send a pump field that is the green one you see here that oscillate as a function of the time, and a non-coherent vacuum that is always present. And then this is transferred into a time-dependent dielectric polarization by means of the crystal that is inside. And so this is the source of the output field. And if you see, this is the output field, and the fact that there is a non-linear polarization will create this correlation between the fluctuation. So maybe a simple way to understand this is that since, I mean, you want to create correlation with amplitude and phase. So if there is, for example, refraction index which depends on the amplitude of the field, so the phase, I mean, the propagation will be affected by the amplitude, the change in the amplitude, so a fluctuation in the amplitude of the field. And so you can, what is going out from the crystal is a state in which amplitude fluctuation are correlated with the phase one. So this will be enough to produce this squeezed state.
Thanks, Eleonora. I'm sorry I have to interrupt. I think we have to
Thanks.
switch.
Yeah, it's much more clear.
Yeah. Thanks a lot. So the next talk is Neil Cornish. Can you stop sharing your